Okay.
Recording in progress.
Okay, then maybe I think most of us are here judging by the numbers from yesterday. So maybe we can start probably now. So we have 5 talks then, and I'm Yongxia. I will be the chair for the first 2 talks, and then Vincenzo will be the chair for the last 3 talks, I guess. So let us welcome the first speaker, Maria Chekova from Erlangen. And her talk is about entanglement between UV C-band and near-infrared photons. So the floor is yours.
Thank you very much for the introduction. Thank the organizers for the invitation. So this work was done in collaboration with a group of Nicolas Joly. And here is, So here is the outline of my talk. I will first explain why we are looking for photon pairs with large spectral separation between the photons. Then I will briefly introduce 4-wave mixing in gas-filled fibers, and the main part will be about our experiment where we generate pairs entanglement between UV, CUV band and visible or near-infrared photons. So we all know that photon pairs and entangled photons are useful for many applications. Here are these just the most important ones: quantum communication, quantum imaging and sensing, and quantum computation. And further, I will only concentrate on quantum imaging and sensing. And namely, there are several fields of that. Based on the effect that was known since 1991, and it was called an induced coherence without induced emission. So what's the idea? There are 2 sources of photon pairs. Each pair is a signal photon and an idler photon. And these 2 sources are coherently pumped so that a pair from the first source is indistinguishable from the pair from the second source. So if signal photons somewhere are brought to interfere, for instance, in the far field, or if we overlap them in a beam splitter, then there will be interference as long as the idler photons are the same for both pairs, and so we cannot distinguish which source emitted this pair. However, if the idler path is blocked by something, or there is absorption, whatever, there will be no interference according to this distinguishability principle. Then we know which source emitted the signal photon, then there is no interference. And this is called induced coherence without induced emission, because there is no induced emission in this regime where it was observed for the first time. And then it allows a very interesting tool for investigating difficult to access spectral range. For instance, if we detect signal photon, which is in some convenient range, like visible or near infrared, its idler twin is what we want to measure. It can be in some other range. And that's why this technique is called measurement with undetected photons. There have been several groups of experiments, of works on this. One big group is imaging and microscopy. This first work by Zallinger group, they placed a cutout with a cat so that photons that were passing through the cutout could create interference pattern in their signal twins. And that's how they obtained this image. And then the group of Ramilov extended it to microscopy, where they even built images of very small objects. This is 100 micron, if I remember correctly. Then the same method can be used for optical coherence tomography. If we put some sample into the idler path that could be, for instance, in the mid-infrared range, and look at the interference of signal photons, then the optical coherence tomography can be transferred to difficult to access mid-infrared range. This was also done by the group of Ramilov. And finally, there can be spectroscopy or Fourier transform infrared spectroscopy, Based on the same principle here, I show the paper of the Singapore group of Leonid Krivitsky, where they accessed mid-infrared range. I'm not sure it's visible, but it's 4 microns. And the same, they just detected visible photons. So in all these examples, the idea is to separate signal photons and idler photons in frequency. And I think extreme in this respect is this work by the group of Georg von Freimann, where they sensed in the terahertz range by registering visible photons. At the same time, what about the UV range? UV range can be interesting because many resonances are in the UV range, and also the UV wavelength is very, of course, very small, so it can offer good spatial resolution. At the same time, this range is inaccessible, at least for spontaneous magnetic down conversion, because to produce a photon in the UV range, the pump should be even shorter in wavelength, and that's not easy. And so our work was aimed at creating pairs where one of the photons is in the UV range. But instead of spontaneous magnetic down conversion, we used another effect, forward mixing, and mainly forward mixing in gas-phase fibers. In forward mixing, unlike in spontaneous magnetic down conversion, 2 pump photons create signal and idler photons. And that's why signal and idler photons are generated like sidebands of the pump photon on both sides of the spectrum of the pump. And this, of course, allows to access the UV range because one of the photons can be even higher in frequency and almost as high as the second harmonic of the pump. The phase matching condition looks like this, except that in fibers, people usually speak of the propagation constant beta rather than K. And this is what happens as the pump wavelength is scanned. There are 2 distinctive regimes, different regimes of forward mixing. One is traditionally called forward mixing. It's where the pump wavelength is at the normal dispersion. I mean group velocity dispersion, of course. Then idler and signal photons are very much separated due to the just phase matching. The other range is anomalous dispersion from the viewpoint of group velocity. And this is usually called, at least in some community, it's called modulation and stability. And here, the phase matching is satisfied due to the Kerr effect. And that's why the higher the pump power, it's shown by red, the dependence for the higher pump power, the separation increases only if you increase the pump power. So the border line is the zero dispersion wavelength. By the way, this plot was sometimes called Pinocchio plot because the higher the power, the longer this nose, but that's just a funny thing. Now, everything depends on the position of the zero dispersion wavelengths. And a great advantage in tuning this is offered by hollow core fibers, so fibers with air or nothing inside. So here, for instance, you see a Kagome fiber where thin, very thin layers of glass or silica glass are surrounding the hollow core. And this is just a picture of how it transmits white light. And the point is that the glass structure itself has weakly anomalous dispersion. Meanwhile, the gas, if we fill it with some gas, here, for instance, the examples are xenon, krypton, argon, and neon, the gas is normal dispersion, but very weak. And so by changing the pressure of the gas, this group velocity dispersion, which is here denoted as beta2, can be varied. And the zero dispersion wavelengths can be changed. Here, for instance, the pressure is 30 bar and the diameter of the core is 26 micrometers. But by changing the pressure, this dispersion can be changed. And recently, for instance, we used this principle to generate photons in a Kagome fiber. Here, the core is shown zoomed in. And we used argon in that earlier experiment. Depending on the pressure of the argon, this zero dispersion can be moved, wavelengths can be moved from 200 to 800 or 900 nanometers. and therefore we achieved tunable signal and idler photons generated in this fiber, very broad tunability, but one photon was at infrared wavelengths, near infrared wavelengths, the other was in the visible range. And in this last experiment, we stepped a little bit further, so we decided to cover the UV range. Well, right here visible, but it's actually near infrared. The fiber we use is a so-called single ring fiber. It's where there are these glass tubes. White is glass, black is air. The core is about 20 microns. Here is the scale. And depending on the gas we put there, this is the zero dispersion wavelength. So we chose xenon as the most nonlinear gas. It provides the nonlinearity, and we see that at a pressure of few atmospheres, the zero dispersion wavelength is about 400, 500 nanometers. We pumped at 400 nanometers, and we expected to see photons at UV. One of the photons, the signal photon, was at the UV wavelengths. So this is the simplified setup. The fiber was kept under pressure. That was changeable and measurable very precisely. And then through parabolic mirrors, through dichroic mirrors, we split idler and signal, sent them to different detectors and to the time header that gave us the times of arrival for the photons. And this is the coincidence histogram, the peak of coincidences versus the delay between signal and idler photons arrival. The coincidences to accidentals ratio is about 400, not very large, but still okay for applications. This is how the coincidence rate depends on the pump power, about quadratic dependence as expected. So what is noticeable here is that we had high level of accidental coincidences. This is really very high for such rates. And that was because of fluorescence in the setup, about dark noise of the infrared detector, and also, as I show in a minute, there were very few real coincidences because signal photons, the UV photons, were leaking out because of resonances. Well, this is the main result, that as we change the pressure from 0.7 bar to about 1.45 bar, we scan or we tune the wavelength of the signal photon from 270 nanometers to 230 nanometers. That's the C-band of UV. And meanwhile, their idler partners are in the infrared, mid-infrared range. These lines, teal lines, show the resonances of the fiber, of this glass, actually. And I will speak about it a little bit more. Then, somehow my font is scrambled here, but this should be idler frequency, signal frequency and idler frequency. So when we say entangled, we are usually criticized that where is your entanglement? I just want to say a few words about the entanglement. The signal and idler frequencies are anti-correlated usually, and there is a measure of entanglement that is the ratio of the width of signal photons, spectral width of signal photons, divided by the conditional width. So if we select idler photons frequency, this is where the signal photons can be. So this is called the Fedorov measure. And we estimated the measure. So this is the calculated joint spectral intensity, so the joint spectral distribution of signal and idler frequencies. We selected the frequency of the signal photon with 4.5 nanometer filter, and then the corresponding idler range was about 40 nanometers. So after that, we increased the bandwidth in the idler range, and although the signal count rate increased monotonically, the coincidences stopped increasing at this point, and this was an indirect measure of entanglement, at least 3, but actually the degree of entanglement is much higher, maybe 30. Right, and then we saw some resonances. As I said, these teal lines are resonances of the fiber. The red line here is the calculation. I forgot to mention it. This is the calculation of the tuning curve, so the dependence of the frequency on the pressure. And you see that it differs from the black line, and the black line would be the tuning curve in the absence of resonances. The points, the experimental points, follow the red line very well, but it shows that we see the effect of the fiber resonances in the dependence of the wavelengths of the pressure. And this is an interesting thing, because in principle we could measure just the signal photons, just the idler photons, not measuring the UV photons. Finally, we also see that the count rate of coincidences has dips, drops at certain frequencies of the infrared, of the UV signal photons, or at certain pressures that correspond to the measurement of these photons. And interestingly, the positions of these dips correspond to the lines of absorption of xenon. But this is, of course, very good measurement. It has to be continued. Before I list my conclusions, I want to thank my group, Santiago, PhD student who did the experiment, Mohammed, who is a master student in this experiment, and of course, Nick Jolie, with whom we collaborate on all related to fibers. And here are my conclusions. So we generate entanglement between the C-band of ultraviolet and the infrared spectral range. We tune the frequencies over 200 terahertz by tuning the pressure. And even we think that we see some UV resonances by looking just at the infrared photons. Thank you for your attention.
Thank you, Masha. So, any questions from the floor?
I have questions. Thank you for your talk. Am I correct that you are using LPHYS'23 for SPDC process?
It's not SPDC, it's for mixing, it's a LPHYS'23 process. Yes, you're right.
Yes, okay. So second question, what is the magnitude of nonlinear coupling coefficient in this case?
Oh, I doubt that I can tell, but I would say it's even slightly less or comparable than that of fused silica. Or fused silica. No. It's much weaker than Chi2, but we here we use pulse light and very tightly focused into this fiber. The core is, as I showed, 20 microns, so the field is higher than typically in SPDC experiments. We actually, I forgot to say something. We see here only about 20 hertz, not more, of coincidences. This is very, very low, but we expect about a kilohertz. It's also not great, but we don't see it because of these resonances in the UV range, and these resonances cause leaking of the UV photons through the glass. We need to design the fiber better to overcome this problem.
Mm-hmm. Thank you, because very interesting talk and questions. There are a lot of other questions regarding the achievement of phase matching condition. So I don't know whether I have time to ask, but again, thank you. Very interesting talk.
You're welcome.
Okay, Dmitry has a question.
Again, thank you, Maria, for interesting talk. I have a technical question. This noble gas atom, they can construct molecule in the excited state.
No.
And maybe fluorescence, you can see the noise. Would you comment?
Oh, yeah. First of all, thank you, Dima, for attending my talk. Thank you for asking the question. We use noble gas and keep saying that noble gases have no molecules, right? And that's why normally such experiments do not show Raman. Usually Raman is a problem. It contaminates the Stokes part of the spectrum. But we keep saying that there is no Raman. However, from what you say, I learned that there is something I don't know about the excited state. I really believe that there is no Raman for noble gas. But I can confirm that this fluorescence is very strange. We do not understand fully where fluorescence comes from. So I don't know, maybe there is something
Okay,
you already
we have to discuss it independently, okay? Later.
Yeah.
Thank you.
Okay.
All right. So in the interest of time, we would have to move on. Let's thank Maria again for her talk. And then let's move on to Joshua Fu from the Stevens Institute of Technology. And he is going to talk about relativistic Bohmian trajectories of photons via weak measurements. So you may start. Joshua, you're muted.
Okay,
Yes.
sorry. Okay. Cool. Thank you for the introduction. As mentioned, I'm a postdoc at Stevens. I'm in the group of Igor Pikovsky, who gave a talk yesterday. This work was done while I was a PhD student at the University of Queensland. And my collaborators for this work, Professor Tim Ralph at UQ and Austin Lund, who's a postdoc at UQ and the Free University of Berlin. So I'm a theorist, and so I guess, we'll get a wide variety of talks today, but hopefully I can connect some quantum information concepts to the background. So I'll just give a summary. I'll introduce Bohmian mechanics in a nutshell. I'll then discuss our paper, which was published in Nature Comms last year on relativistic Bohmian trajectories of photons. And if I have time, I'll discuss some extensions to that work to multiple photon interactions. So if you are not familiar, Bohmian mechanics is a deterministic, non-local, hidden variable interpretation of quantum theory, rather than the wave function giving some probability amplitude for where you would find a particle. In Bohmian mechanics, psi is interpreted as giving rise to a guiding potential that governs particle dynamics. And the additional assumption of determinism means that, particles are interpreted to follow deterministic trajectories through space-time given some initial distribution. Like any good interpretation, Bohmian mechanics recovers many of the standard predictions of quantum theory, such as the Born rule. So when you have psi squared, you have now some density of particle trajectories given some initial distribution, as opposed to a probability density. But Bohmian mechanics has sort of fallen on hard times due to its apparent incompatibility with relativity. So, for example, it's often thought that you invoke a privileged spacetime foliation when you propose this quantum potential that is defined across all space and basically picks out a preferred reference frame, which is of course incompatible with the idea of relativity and in the principle of relativity requiring that there's no preferred reference frame. So I'll point out that most studies report that 0 to 2% of physicists prefer Bohmian mechanics as an interpretation, which probably makes 0 people in this Zoom call. So just to ground this in some equations, what is usually done is a polar ansatz is invoked for the wave function with some amplitude r and phase s. And this gives rise to this Hamilton-Jacobi type equation where you've got some classical part of the dynamics and then a quantum potential part, which is supposed to give rise to the quantum dynamics of a particle in some unusual potential governed by R. And this gives rise to an equation of motion similar to Newton's laws, like you'd have a classical force guiding the particle, but in addition, you have some quantum force that arises from this potential. So in 2007, Howard Wiseman put out a paper which reinvigorated interest in Bohmian mechanics when he connected this sort of abstract interpretation of quantum theory with a measurement protocol based in weak values. So what he did was he proposed a way to measure the average trajectories of non-relativistic particles by taking the weak value of their momentum divided by mass to construct a velocity field. And he showed that this is equivalent to a more Bohmian type expression, which is constructed from the components of the conserved current. So you've got your conserved current and your conserved current density giving rise to a velocity. And he showed that these two expressions are basically equal. And so for those who are not familiar with what a weak value is, it is the extension of a weak measurement, which is a measurement that only minimally disturbs a system, but comes with a lot of measurement uncertainty. However, if you do a lot of weak measurements on an ensemble and then you post-select on a particular outcome, then you can obtain the average value of the observable you're interested in with arbitrarily high accuracy. So the notation here is that we have some initial wave function, psi, we evolve the system, and then we weakly measure P, and then we post-select on some final state of the system, which is here an X eigenstate. And then the additional, so Howard's weak measurement framework would give you some average trajectories of photons, and then the additional assumption of determinism gives rise to a Bohmian type interpretation of the trajectories of these photons. So just for those who maybe not be familiar with the process of weak measurement, I'll just give a quick tutorial. So in our usual measurement theory, we have some pointer variable in our system with observable S that we're interested in. We couple them via this interaction. We measure the pointer in some arbitrary basis, post-select on some final state of the system, phi, and then because we're assuming that the interaction is weak, we expand to linear order, and then we take this term to be our weak value, perturbation to the evolution of the system and pointer together, and we take the real part of that to denote that we're interested in a conditional average of this measurement. So this was a significant work because it gave rise to some very influential experiments. For example, this one, I think by the group of Ephraim Steinberg in Toronto, were able to map out the average trajectories of photons in a two-slit interferometer. And when I say photons, I still mean non-relativistic particles insofar as the transverse velocities of the photons is slow. So you can see that the photon, each black line corresponding to a trajectory of an average trajectory of a photon, they did their weak measurement protocol and mapped out the velocity field of these particles. And then you can see that the particles seem to bunch up in regions of constructive interference and avoid regions of destructive interference. You can consider this sort of be like a space-time diagram. So this was a significant achievement, and it was extended to 2 particles by, I think, another group. So we asked the question, can we extend Howard's framework to relativistic regimes and ground the Bohmian trajectories of photons in a measurement framework that circumvents typical pathologies of the theory? So starting with the relativistic definition of velocity, we propose a recipe for measuring the average trajectories of photons with weak values. So we construct our relativistic velocity with the components of a 4 vector, and then we come up with this definition, neglecting factors of C. We've got your momentum divided by your energy, and we propose that we can weakly measure P and weakly measure the energy of the photon, and we consider the initial state to be in psi and then post-select on X and get these measurements simultaneously. And then from the theory perspective, let's just assume some relativistic dynamics. So for that, we can take some Klein-Gordon theory. We can make some simplification by taking a scalar theory, which just reduces the calculations a little bit, but inherits all the Lorentz covariant properties of photons. And we showed in our paper, whose reference is here, that this measurement framework gives rise to a standard velocity in Bohmian mechanics, or in even standard quantum mechanics, where now you've got your conserved current of the Klein-Gordon theory, and then your conserved current density from that same theory, and that's defined as this, which has now has first derivatives in space and in time. So just some features of this equation. So the components explicitly satisfy a quantum mechanical continuity equation, which is nice, which means that it's consistent with standard quantum theory. Probability density is conserved, and the velocity transforms covariantly under boosts. So it satisfies a relativistic velocity addition rule. And this is sort of almost by construction, because these components of the Klein-Gordon conserved current form a 4 vector. Now, just to ground this in something more concrete, let's consider a concrete setup where we've got a sort of like a Mach-Zehnder interferometer, or a Michelson-Sagnac interferometer, I should say. We've got some single photons hitting this beam splitter 50-50, or it's adjustable, I guess. And typically, we'd consider the wave function to coherently evolve through both arms of the interferometer and then interfere and produce some fringes in the middle here. But now in the Bohmian interpretation, we are interested in mapping out the trajectories of single photons hitting the beam splitter and taking either the upper path or the lower path, and then seeing their behavior in this middle region. So I should mention that the experiment that was undertaken for the two-slit interferometer is more akin to something out here, where now you have these slowly dispersing trajectories in the x direction and a large momentum in the z direction. So some final details, we consider our initial state to be some Gaussian pulse in potentially a superposition of left and right movers. Our dispersion for the photons we assume to be massless, or in the z direction their momentum is very small. And then we post-select at some position. So we have our detectors at some x, and we scan through different x's, and we run this experiment over and over again, or this theoretical experiment over and over again. And then we obtain some velocity equation and solve that with some initial condition of the photon. And all this detail is outlined in the paper. So these are some of the plots that we get. On the left, we've just got some Gaussian pulse moving from the left to the right, and each white line corresponds to a different initial condition of a photon where we place it in the pulse. And as you can see, the underlaid is the probability density that you would typically obtain in a photo detection experiment. So that shows some probability density. And as you can see, the density of trajectories, when you distribute them in some appropriate way, matches up with the probability density itself. On the right, we've got some superposition of right and left moving waves. So now we have interference, and again, the density of trajectories matches up with the probability density of the wave packets produced by standard quantum theory. But interestingly, the trajectories start to avoid regions of destructive interference, and they bunch up in regions of constructive interference. Moreover, in these units where c is equal to 1, you can see regions where the photon starts to move faster than light. And this is a feature, not a bug, of our theory, insofar as we are constructing this velocity field of the photons as some coordinate velocity in a particular reference frame. So in general relativity, there's no problem with coordinate velocities exceeding the speed of light from a coordinate sense. Of course, locally, a photon will always travel at c. Also, you might be interested to see that the photon stops and turns around, which is not what we typically understand photons to do in a standard interpretation of quantum theory. We can boost to a new reference frame, and because this Lorentz boost couples x and t, we now have a time-dependent interference pattern. Importantly, the regions where the photon was superluminal in the original frame can now point towards the past. And again, this is consistent with our understanding of weak values, insofar as a weak value of an operator can lie outside the usual spectrum of that operator due to this weird post-selection mechanism. So basically, underlaid, the probability density we associated with essentially the energy density of the photon, and we're taking a weak value of that. So what this is saying is that the weak value of the energy density can be negative. And this was one of the pathologies of relativistic Bohmian mechanics typically understood, with abstracted away from a concrete measurement protocol. And this is basically me explaining that. However, I should make the caveat that when we have the probability density, this weak value of our energy, is actually positive definite in the regime where which we typically consider in quantum optics, where your wave vector is much larger than the spread of your frequencies. So your pulse is very far from the origin, and there's no impingement upon the negative frequencies. Such an impingement where you have your Gaussian tail going into the negative frequencies would signify some coupling between negative and positive frequencies, which is typically associated with like a subcycle regime where you have particle reduction from the vacuum. So given that we are considering a single particle theory, this is all very consistent and means that there's always a reference frame in which all of your tangent vectors of your velocity field are pointed towards the future. So our theory reduces to Howard's non-relativistic result when we take some paraxial approximation, when we take our momentum in the z direction to be very large, and this looks sort of like a free massive particle where you've got p squared on 2m, where kz is an effective mass. and the Klein-Gordon density reduces to your typical psi-squared. And these are some trajectories. Now the photons obey have some dispersion in space-time, but all of the predictions match up with what we typically expect for a two-slit interferometer like the Cox's experiment. So in standard Bohmian mechanics, you have this additional object, the quantum potential invoked, which pushes the particles around through space-time and acts a force upon them. For massless photons, we need to generalize this to something of a geometric nature. And so we came up with basically a space-time metric as an interpretation of how these particles move through the experiment, insofar as the path they take can be interpreted as the geodesic path that they follow in a space-time geometry. And such a space-time geometry needs to give rise to, for example, space-like tangent vectors. So we chose this exotic Alcubierre metric, which is a warp drive solution. But interestingly enough, if we choose this free parameter Vs to be this, where V is our Bohmian velocity, which we measure, then you find that the coordinate velocity obtained from this metric is exactly our Bohmian velocity. So one way to interpret these trajectories is that you have some exotic space-time metric, which is sourced by some wave function, and it gives rise to these exotic trajectories that can stop and turn around and become superluminal. So I'll briefly touch on extending our framework to two particles. So this is in a forthcoming work where we extend it to two particles. So now we've got two lasers. They are directed towards each other. We've got two detectors now, and they don't know the identity of the particles. So this introduces some indistinguishability into the detection process, and we need to post-select on simultaneous coincidences on both detectors and then symmetrizing this process. And long story short, our velocity equation obtained from a weak value standpoint is equivalent to one obtained from a more formal Klein-Gordon approach. And hopefully this should be on the archive in the next month or so. And these are some of the trajectories. Each color corresponds to a pair of photons. They appear to interact non-locally. However, this can also be interpreted from a purely local standpoint, where the wiggles of the trajectories only begin when the fields corresponding to each of the photons start to overlap. And I don't have much. Yes.
Yeah. You have about 2 minutes.
Okay, no worries. Yeah, and I'll just show a probability density plot. So this is, again, similar, but now each white dot corresponds to a pair of trajectories in some higher configuration space. But this is what we typically expect. So because the photons are indistinguishable, either the photon number one is at position 1 and photon number 2 is at -1, or vice versa. And this is at some time outside of the interference region. And then we can also consider the time when they are interfering with each other, and we've got some correlation between them due to the fact that we're introducing this weird post-selection on both of the particles being detected at one of either of the detectors. But I won't go into too much detail. Just to summarize, we extended Howard Wiseman's weak value framework to incorporate relativistic dynamics of photons. I should mention that the framework is independent of the form of the Hamiltonian, so we chose a scalar Klein-Gordon theory, but we could have applied this to Dirac particles or to a vector theory for electrodynamics. And then we plotted the trajectories of these photons in a Michelson-Sagnac interferometer, and it's all consistent with standard quantum theory. And this provides a measurement framework that can, in principle, be implemented in the lab. So I'll end it there. Thank you for your attention, and yeah, I welcome any questions.
Okay, thank you. Any questions? Or maybe if nobody wants to ask something, maybe I can ask a very potentially naive question. And I think this question is sort of an HO question when it comes to Bohmian trajectories. And that is, if you were to assign trajectories to quantum particles, let's say photons, would it contradict the notion of genuine indistinguishability of, between two particles? Do you see a problem in this respect?
As in the fact that each particle follows a unique trajectory, and that sort of picks out a preferred identity of that particle. Well, I think that I don't think necessarily that's the case. In our 2-photon example, for example, we in our equations we identify particle A to be one of the particles and particle B to be the other particle, but ultimately our detector doesn't know. The label A and B is sort of arbitrary, and it's sort of meaningless from the framework of an experiment. Like, there's no point saying that this is this particle and this is this particle. Yeah, I'm not really sure how to answer that any better than that. But I don't think that fermion mechanics forces one into that position. Yeah.
Okay.
Yeah.
So let's thank Joshua again, and then I will hand the baton to Vincenzo as the chair. Vincenzo?
Hello?
Hello.
Hi, I'm here,
Hi.
yes.
Okay,
Let me see
so
if this work, yes.
okay, so
all right.
I will be signing off. Thank you.
Yes, no worries. Let's see here. All right, so the next talk is Dr. Piacentini. Fabrizio.
Hi, Vincenzo.
Can you share?
I'm here.
Yes,
I will share my
good.
screen right away.
Yes.
Okay.
So so you have 20 minutes. I can give you a 5-minute notice, or you like me to give you a notice?
Sure.
All right. Sounds good. Okay. So so the talk.
Let's see whether you can see my.
Yes, perfect. You just by the presentation mode.
Yeah, but you're not seeing the right screen, right?
No, I see. Yeah, I see you. What you should see it. Yeah, just do the standard presentation mode.
Yeah, it's just that I have to switch screen, and I never can remember how. Okay.
Perfect. Yes. So single pair measurements of the Bell parameter, certifying entanglement without destroying it. Go ahead, Fabrizio.
Okay.
Thank you.
Thank you, Vincenzo, for a nice introduction, and thank to the organizer for giving me the chance to speak at this nice seminar. And this is exactly are you seeing the presentation properly, or you see it cut on the side?
I think it's okay. Oh, wait a moment. There is on the left side, I see something because you have a slide on the left.
Yeah, so I will just interrupt the sharing, and I do something different. Okay, so here I can. Okay, now I will share it again. And now I think you see it clearly, right?
Yes, go ahead, yes.
Okay, sorry for the small issue, but I will not ask for further time. Well, everyone knows here the EPR paradox, a celebrated paper from 1935 by Einstein, Podolsky, and Rosen that actually argued that since there is no possibility in quantum theory by the description of usual description with the wave function to assign to every physical element an element of reality that is something that can be predicted with certainty without disturbing the system, one has to conclude that the description of reality given by the wave function is not complete, because you cannot predict with certainty and arbitrary precision every element of reality in your theory. That means that that is due to the fact that there are non-computing operators, non-computing observables. So how can we recover completeness? Well, completeness can be recovered by adding hidden variables to the model. Hidden variables that are variables that cannot be accessed by us, but anyway, with this we can reconstruct a classical theory that is complete in the sense by Einstein, Potocki, and Rosen. And what if you want to add locality? Then, if you add locality assumption, you have local hidden variable theories that are exactly the ones that can be tested by Bell inequalities. So, you know that if you, as I anticipated, Bell inequalities are the tool that allows you to discriminate between quantum mechanics and LHVTs. Why? Because there are predictions by quantum mechanics that are different with respect to LHVTs. And these predictions are related to entangled systems and can be computed can be observed by computing these, by evaluating the quantities in these Bell inequalities. Okay, for example, you know that quantum mechanics has non-epistemic probability description of the laws of nature. It's an intrinsic probabilistic description, while HVTs is epistemic, because the probabilistic behavior that we see in our experimental outcomes is entirely due to the fact that we don't have access to the local hidden variables. Then we have uncertainty principles on quantum mechanics on non-commuting observables, while we have on the LHVT side a classical determinism that classical physicists would love, of course, that is recovered also for microscopic systems. Quantum mechanics, nonetheless, shows some traces of incompleteness. We have non-locality. We have the problem of macro objectivation that is pushed further and further by current experiments. We have the measurement problem concerning the wave function collapse and so on. While LHVTs are essentially free from this kind of issues or traces of incompleteness as you want to see them. So in 64, John Bell just says that, okay, let's stop with the philosophy and let's go to some experimental find some experimental evidence, because there are some quantities, some inequalities that must always be satisfied by in LHVTs by construction, and these same inequalities can in some conditions be violated by quantum mechanics. So if we manage to violate this inequality, if we find a violation of the inequality of these inequalities, LHVTs must be discarded and should be falsified. And the path of LHVT's study from the very first experiment towards the Orsay experiment with the first space-like separated photons and the quite recent loophole-free experiments was actually deserved the Nobel Prize last year. As you can see here, you have Alan Aspect, John Clauser, and Anton Zeilinger from left to right that have been awarded the Nobel Prize. So no luck for us. Let's say we will have to find something else. I'm joking, of course. Well, let's study one of the most celebrated inequalities. That is the Clauser-Orne-Shimony-Holt inequality from 1960. It's a 4 settings reformulation of the original one, because the Bell one had 3 settings, but it was almost impossible to test in a lab because it would have required perfect correlations among measurements. Okay, here instead we have an inequality of this type. We have Alice and Bob. 2 entangled particles are separated and one goes to Alice and the other goes to Bob. And if we compute these quantities, this algebraic sum of these correlators that in LHVTs can be computed like this, when you can observe the space-like separation, the locality principle, that means that the 2 probabilities on Alice and Bob's side have to be independent of each other. They depend only on the lambda hidden variable distribution, let's say. We can compute that quantity that has to satisfy that bound, that is the absolute value of this algebraic sum of correlators must be less than 2. Of course, in quantum mechanics, we can compute the same correlators, as you can see here. And we found that in quantum mechanics, the bound is different. We have the Zierelsson's bound that says that for the same quantities in quantum mechanics, have to satisfy a bound that is 2 by square root of 2. So they can be the correlations can be in some sense stronger. And if we find something that is above 2, but of course below the Zierelsson's bound, because by construction, again, the Zierelsson's bound is the highest bound that we can reach, the highest value that we can reach in quantum mechanics, we can say that we violated the Bell inequality, the CHSH inequality in this case, and we can, in some sense, discard the local hidden variable theories. Of course, since we have wave function collapse and uncertainty principle on non-commuting observables, each single pair can give information on just one of the correlator constituting S, because as you can see, both Alice and Bob get to choose between 2 different measurement settings, alpha 1 and alpha 2 for Alice, beta 1 and beta 2 for Bob. And each pair, when I perform a measurement, of course, in the usual traditional projective measurement framework, the entanglement is destroyed. So I can randomly choose between alpha and beta, and that's all. That's all. Each pair can give information on just one of these 4 correlators, building up the CHSH inequality. But is this really true? Isn't there a way to somehow get information on everything? Well, of course there is, but you have to switch a paradigm shift. You're now in the projective measurement paradigm shift. That means that if you have projective measurements in a sequence, of course you can't measure something like this, because what you measure is actually this, right? Because you have the wave function collapse. The second measurement hasn't been performed on the same quantum state. It has been performed on the collapsed state. So, what in a traditional Bell inequality test, what you have is this scheme here. You have Alice and Bob, both randomly choosing between alpha 1, between their settings alpha 1, alpha 2, or beta 1, beta 2, and then they compare their results. They compute their coincidences, they compute their correlation coefficients. But essentially, of course, for each entangled pair, there is one specific setting on Alice's side and one specific setting on Bob's side. So to estimate the S parameter of the CHSH inequality, Alice and Bob have to randomly choose their measurement settings in each experimental run, and multiple runs are required. Oh, sorry, I was already spoiling. But we could, as I said, as the title of the slide suggests, we could pass from projective measurement to weak measurements. Weak measurements have been introduced in the 1988 by Arno, Adalbert, and Weidmann. Little information is extracted from a single measurement event, but the state does not collapse. And given the much recent introduction that Joshua gave about weak measurements, and I thank him for doing that in my place, I will just skip the concept of weak value. That is some sort of some generalization of the expectation value between a pre and post selected state. We have von Neumann coupling as he presented, then a projective measurement that is the proper post selection that we have, and we can compute this out thanks to the output state, the weak value, or at least the real part of the weak value, by looking at the observable canonically conjugated or to our pointer observable in the von Neumann coupling. So far so good, but we don't require only weak measurements. For what I need to do, I need joint and sequential weak measurements, because weak values, as I told, challenge one of the canonical dicta of quantum mechanics, that non-commuting observables cannot be simultaneously measured. Because the fact that the state does not collapse during weak values allows you to perform multiple measurements, even on non-commuting observables, onto the same state. And depending on the kind of Hamiltonian you construct, you can have joint weak measurements when the Voigt-Neumann coupling takes this form here, and the result of the correlation between the two conjugated the two conjugated meters is reported here, and sequential weak measurements in which there is a proper sequence between these measurements, and what you obtain is a slightly different result. Here you don't have a single unitary operator, you have a composition of two different unitary operators, and the result is a little bit diverse. And what happens when you do sequential weak measurements on a single photon? Let's restrict our case for simplicity to linearly polarized pre and post selection photon states. We have this framework picture here. As you can see, here you have the first Voigt-Neumann coupling, the first weak measurement, weak interaction, let's say. Then the second, we have a half-wave plate that rotates the polarization space for the second measurement. And if the coupling of these interactions, that means JX and GY, are weak enough, what you obtain is this feature here. Let's restrict ourselves to the case in which pi alpha 1 is the projection in the vertical direction. Then we have the projection on an arbitrary axis, the axis rotated of an angle theta with respect to the horizon. What you obtain is this picture here. You can compute the single weak values and even the weak value of the product of the states. And that's already a surprise because the product of the observables, sorry, because the product of observables, it's not mandatorily an observable. It might be even something else. And this is what we obtained. Yeah, sorry?
5 minutes.
10 minutes?
Five.
Five, okay. Then I will switch. These are the results with some very nice product rule violations, where, as you can see on the right, we have that a positive number by a negative number gives a positive number. So what we learned at school is wrong. And sequential weak measurements have already been used for example, for violating a multiple measurement Legge-Garg inequalities. So we have just to duplicate that setup like this. And here we have Alice and Bob having the same structure as before, so two weak measurement in a sequence. And we here, instead of that case, we don't do any post-selection. No post-selection is done. So the weak measurement outcome gives the expectation value of the measured observable. It's a simpler case in some sense. This is an actual pictorial scheme of our setup. As you can see, we have an entangled pair source. We have our birefringent crystals performing the weak interaction, the half-wave plate that allow us to perform the measurement that we want. We produce some very high-quality entangled state. And this is the correlators as a function of the coordinates that we get outside, because we have two x coordinates and two y coordinates, one per side, of course. So we end up with this fourth-dimension coincidence count. And if I perform compute the correlation between these elements, what I obtain is exactly this information on the whole Bell parameter. So each entangled pair gives information on the whole Bell parameter, on all the correlators forming it, actually. So let's see some results. Here is the lot of experimental points that we did. Each point corresponds to a single pair detected. Okay, so this is their distribution, and this is their histogram. Of course, the uncertainty is very wide and very big. Why? Because the fact that the interaction is very weak and the state does not collapse corresponds to the fact that you have a very low information. That means a very huge uncertainty on the single measurement. But if you perform a good average, what you obtain is this. A quite strong violation of the LHVT bound. And in each case, I obtain information, I extract information on the whole Bell parameter without destroying the pair. And I show you why, without destroying the entanglement, sorry. And this is the part, this is the topographic reconstruction between of the two photon state before the measurement. So a very nice singlet state with a very high fidelity. and a quite high purity. And this is the state. We have the computer, sorry, negativity and concurrence. So we have a good estimation of the entanglement we had initially. And this is what we obtain if we perform tomography after the 4-week interaction have been performed, after we performed the Bell measurement. So as you can see, we have still a very high fidelity, still a very high purity, although some disturbance has been induced, of course. And so the entanglement is still there. I can still use it for something else, for a quantum communication protocol, or for some quantum sensing protocol, for whatever I want, for other foundational tests. So in summary, we realized the first single pair Bell inequality test, able to extract a Bell parameter value for each entangled photon pair measured. We do this by resorting to weak measurements. And this approach stretches the concept of counterfactual definiteness, because otherwise we should perform some even in loophole-free tests, we perform some counterfactual reasoning on the Bell inequality tests, because we assume that the probability space remains always the same for each measurement. That's not something that can be somehow granted. And aside of that, we have a technological improvement by this kind of framework, because we have a non-invasive entanglement certification. And this can boost the performances of the quantum technology protocols, for example, the Eckert's protocol, or the device-independent realizations of other protocols that require sacrificing multiple pairs for sensing entanglement. But here we can perform this entanglement certification while undergoing the protocol. Next step, of course, well, we have something to do, and with this, I thank you for your attention, and I thank all the people that gave their support for this work. And okay, I'm happy to take questions.
Thank you, Fabrizio. Just a quick question. Let's see, Masha, please.
Thank you, Fabrizio. The talk, it was really very clear. But I have a question. You say it's a single pair, but you need to repeat this measurement many times. So
yeah, sure. Like,
what's the point of a single pair?
The point is that I can estimate the whole Bell parameter on a single pair, not just one of the correlators. I'm able to estimate all the 4 correlators forming the Bell parameter for each pair. So I'm measuring something that doesn't even qualify as an observable. It's not even an observable. I repeat my measurement just to have a better statistics, of course. But if I allow me to have a huge uncertainty, each pair gives me an estimate of the whole Bell parameter, something that no experiment so far could do.
Okay, thank you.
Very quickly, Sebastian, please.
Yes. Would that be equivalent to do a POVM interferometer that would have main outputs that to implement all the multiplication of observables?
No, because in that case, each pair would be undergoing one of the POVM elements. But here I'm sensing, I'm doing all the measurements at once, not statistically one of them. I mean, it's no strong measurement framework can qualify to replace this kind of, as far as I know, at least. But I'm happy to discuss it.
Thank you.
So I'm afraid that we need to move on. Sorry, Dimitri, maybe we can have further discussion afterwards. But we need to keep the schedule. So
okay, I will stop sharing my screen.
Yes. So let's move to the next speaker. That is Dr. Shaukat.
Thank you, Professor.
So
can you listen me?
Yes, that's good. So you will be Dark Solid on QDITS, a novel quantum information platform. Please.
Yes. Thank you, organizer. Thank you. First of all, thanks, organizers, for giving me this opportunity to present here. So, as all of us very well know that quantum information theory is a rapidly evolving subject which involves the study of achievable events possible within quantum mechanics and may have lots of surprises waiting to be discovered. For those reasons, we thought to make some physical model for which it is possible to describe the distinctive possibilities of information processing. And for that, we choose dark solitons with Bose-Einstein condensates in quantum information theory. First of all, I will describe very briefly what is soliton and how to obtain zero density dark soliton. Then I will divide my presentation into two sections. In section 1, we will discuss how the impurities can be immersed with the Bose-Einstein condensate to create the building blocks of information processing and what will be the lifetime of this qubit or the qubit. Then in section 2, we will see that can we place two dark solitons together, or is there any force or the repulsive force, or what will be the effect of the repulsive force in that one. And in accordance, we will see the spontaneous generation and the phase gate between the two dark soliton qubits. At the end, I will summarize my results. John Scott Russell in 1834 made a discovery of the wave of translation that gave birth to the modern study of the solitons. Basically, he observed that this wave has a permanent shape that can travel over larger distances without changing its shape. And also he observed that it does not obey the superposition principle. Then the scientists have a question in mind, why and how all this happened. To find the research was going on, and later on the researcher determined that this all happening is due to the precise balance between the dispersive and the non-linear effects in the system. If you will see that this, which the scientists named as a solution of many non-linear differential equations like Sine-Gordon equation, Korteweg-de Vries equation, and Gross-Pitofsky equation, which is the main concerned equation of my presentation here. Here, GB, which is a non-linear coupling, can be a greater than zero or repulsive or attractive. In other words, with the repulsive interaction, we will have a dark soliton. With the attractive interaction, we have a bright soliton. In accordance, we consider the state of matter Bose-Einstein condensate, where we consider the repulsive interaction between the particles and represented by this Gross-Pitofsky equation, whose solution in terms of the soliton can be represented here, which you can see here, where N0 is the number density of the BC particles, and here theta, which is represented by V over Cs, that means the V is the speed of the soliton. For the very simple case where V can be zero, V cannot be zero, but we are considering very simple case where V equal to zero. This means that the amplitude is going to the completely zero node. So it means that this is called the zero density dip dark soliton here. Very simple solution. However, if we go V is not equal to zero, V is approaches to Cs, this amplitude is going to be decreased. And if V equal to Cs, there will be no soliton existence here. Fortunately, the researchers have already seen this experimentally as well, which you can see here on the figure here. So now the question comes in our mind, okay, this is a soliton existence in a BC, also experimentally it is verified. So what should we do to see the two levels, to separate exactly 2 or 3 levels in a system, to see the building blocks of quantum info processing, to use it as a qubit or a qubit. And for that, what we did is basically we immersed Bose-Einstein condensate with a set of the impurities here. But particularly here, it is very important to note that these impurity particles, what type of impurities we need to consider, this is very important point here, which you will see in some equation. Why I am saying that this is important, because which atom we have to use, that one, that plays very important role to exactly separate the 2 levels or the 3 levels in a system. Here the wiggly lines shows the quantum fluctuations, and this shaded region is the soliton, which you already seen that one. And this whole system is represented by this coupled Gross-Pitofsky equation, where G11 is the interparticle of the BEC components interaction, G12 and G21 is the interspecies BEC and impurity particles interaction. Here we have considered a very G22 is equal to 0. We have considered that the impurity particles are not interacting, because then the soliton will not perturb due to the presence of the impurities. And also the impurity particles are assumed to be much dilute and much massive than the BC particles. So the soliton act as a potential for the BC particles here. After solving a lot of mathematics, obviously there's a lot of not a lot of mathematics, basically just using very simple calculations, we can determine this energy spectrum here. where n is the number of the bound state and nu is the parameter with which is depending on the interspecies to interparticle or the mass ratio of the impurity and BC particles here. What I was telling you that impurity particles, we need to think about what type of impurities we need to use that. If you will see that there is a mass ratio M2 over M1 comes with you to that partner, or the G21 or G211 is an interspecies company coefficient also appears here. Now going beyond that one, if we somehow manage that what type of atoms we should use and what are doing some simplifications, we see that if nu is going to be in the range of 1/t to 1/3 to 4/5, then suddenly two levels appear here. And also these are the analytically also verified that we determined this harmonic oscillator solution with respect to that one. But there is a degeneracy at some new point is equal to 1/2, at which the qubit is ill-defined, which you will see in the next slide here. The natural question comes with that, if we go beyond 4/5, then the third level appear for sure, which you can see here. Now, simply anyone can think that if we go beyond 9/7, then the fourth level appear. If we go beyond that range, then the fifth level appear, and so on. But before that, we need to check that is this experimentally feasible to see that phenomena or not. And for that, we did some simulation, a numerical check with respect to that analytical expression. If we see that the ground state and first excited state, our results of the numerical analytical results exactly matches. However, for the second excited state, there is a little mismatch between these states for the third level state. So it tells us that the impurity particles are playing very important role here. So it means that if we go beyond 3-level system, maybe the 4th level system will not appear, or if it will appear, it will completely mismatch between the numerical and the analytical results. However, that we can manage somehow if we see the M2 over M1 is equal to 1.56, which I am using here. If we go for some other atom, then we can use that atom in accordance to that to mismatch, to clarify that mismatch between the states, or to get this result for that one. So in order to find obviously, whenever we have that qubit, so it's a very important question that comes with that, what will be the lifetime of that qubit? In order to determine that, first we consider that the dependence of transition frequency with respect to the interspecies to interparticle interaction for the range of the qubit, which is 1/3 to 4/5. This shaded region shows you the range of that qubit, basically, and where you can see that at one point at around 0.5, where the qubit is ill-defined. We need to see that the spin up goes to spin down, and spin down goes to spin up, very similar to that one. And for the carrier, to find that one, a lot of mathematics obviously involved here, which I am not explaining here. We obtained this quantum optics Hamiltonian to make it an open quantum system, like sigma is the system operator, 2-level system operator, and bk, which are the quantum fluctuation in the BC, makes an environment for that 2-level system. So it consider GK is the coupling between these two, and that makes an open quantum system basically. But to find this quantum optics Hamiltonian, we use the rotating wave approximation and the resonance condition to ignore the intraband terms here, which we have already done that one. Similarly, for the 2-level system, it will be easy to determine that one now. And for the 3-level system, if we do similar work with respect to that one, we will get the similar Hamiltonian with respect to that one. Now comes to the lifetime of that qubit, we employ the Wigner-Weisskopf theory to find the lifetime of that qubit system, where this alpha denotes the amplitude of the excited state and gamma is the spontaneous decay rate, depending on the coupling and coupling coefficients or the interspecies to interparticle interaction here. And here, if you will see that this again shaded region determines the 2-level system range. And if we see that part here, if we use some few kilohertz of chemical potential, we determine the lifetime of that qubit, which is of the order of the second, which is much, much better than the other all available matter wave qubits already predicted here. So now comes with this question in time, we have implemented the rotating wave approximation. Is it satisfied or not? We can see that gamma is much, much less than the transition frequency. The rotating wave approximation is also satisfied. So it means that the Hamiltonian, which we have determined, verified in accordance to that one. However, there is a major limitation to our model is the quantum diffusion, due to which the qubit lifetime can be decreased by 20% due to the presence of the background fluctuations in a system. But it is not to be worried, because I have already calculated that one, and I have already determined this lifetime in terms of the 0.1 second by calculating this quantum diffusion effect also. But then there are just I want to mention here that this is not just a one theory, Wigner-Weisskopf theory. This is not, I would like to mention, in fact, here that Wigner-Weisskopf theory is not just a one theory which we can use to determine the lifetime of the qubit. There are other theories which we can use, and for sure that is equally valid, which you will see in a few minutes later. Similarly, doing the very similar mathematics, we can have this three-level system dynamics very clearly we can determine. It does not need to be explained here. Due to this long lifetime of our qubit, the editor of the physics APS has decided our paper for the physics synopsis, and he mentioned that here this qubit ranks near the top when compared to the lifetime of the existing matter-wave qubits. It is within a factor of the 10 of the lifetime of that qubit that have already been perfected in the lab. So now, after finding the lifetime of the qubit, the first question, another fundamental property of the quantum information theory, which is the entanglement dynamics. And for that, we have to see what we have done. We place the two dark solitons together in a BC having separation D. But the first question comes in our mind, do they not repel each other, or is this repulsive force strong enough to disturb this soliton location or not? And for that, we choose some short-range potential of this particular form, and we have seen that the maximum displacement is 0.09 d, which is much less than the distance between these two qubits. It means that it is ignorable. But to check that numerically, we did some simulation by placing 24 solitons together in a system, and you can see that the inner solitons remains almost the same at the same location. However, the outer solitons have some disturbance in that part, so which restrict our model to the 20 solitons together in a one system here. But that means that we can play for the 2 or to maximum of the 20 qubits almost to play with that system here. Again, doing a lot of mathematics, we can determine the interaction Hamiltonian for the open quantum system for this system as well. Now comes to the entanglement dynamics. To determine that one, we use now the Markovian approach, master equation. We derive that master equation by using the Markov-Born approximation or other simplifications, which does not need to be defined here basically. And where eta ij is the qubit-qubit interaction, which is very weak in our system. So I'm not representing any results of that one here. But gamma ij, where I can be equal to j, I cannot be equal to j. If I equal to j, that gives us spontaneous decay. I not equal to j, that comes with the collective damping resulting from the mutual exchange of the mediating particle between the two dark solitons here. That shows, if you will see this figure, that shows a very non-trivial decay with respect to that distance here, but that plays very important role to determine the entanglement, to generate the entanglement within the system here. And to see that, or to solve this master equation, we use the collective or decay state, where the two-level system make a 4-level system to see the superradiant and subradiant effect basically. And symmetric state is, or antisymmetric is a maximally entangled state here. Gamma plus gamma mean to say that the superradiant or the fast decay, gamma minus gamma mean to say that the antisymmetric state or the subradiant state or the slow decay, which we can see from the density matrix elements as well. However, in our system, if we will see that at d is approximately equal to 5 over 2 xi, this means that gamma, capital gamma, which is the collective damping, is going to be the negative, which tells us that our system S, which is generally is a superradiant state, becomes a subradiant state, and subradiant state becomes a superradiant state in our case here. And for that, which is very good to see that phase gate here, which we have implemented in on our next 1 or 2 slides here. And to observe this spontaneous generation entanglement between the system, we employ the...
It's 5 minutes.
Sorry?
It's 5 minutes.
5 minutes, okay. Well, I have. To generate the entanglement, we consider the superposition of the symmetric and antisymmetric state and employ the Wurter's criteria to observe this concurrence here. where this eta, which is the qubit-qubit interaction, it comes with the sign term, which tells us as the oscillation. And we can see there is no oscillation in our system. So because of this eta is very, very weak or very, very small. So that's why we cannot see any type of oscillation. However, gamma, which is the collective damping that generates the entanglement, where this concurrence displays the very fast increase, follows very slow decay, and it has a larger value at larger distance, which is very good for our case. And this all happening is due to the discrepancy or the between the two cascades, like excited to symmetric, symmetric to G decay, excited to antisymmetric, and antisymmetric to G decay. That comes with that one here. And at the end, it reaches to the symmetric state. And if you will see that my point, that one symmetric state, which is generally is the superradiant state, becomes a subradiant state in our case here, which you can see very clearly in this figure here. So now comes to see that if we can we have the steady state concurrence to verify our results at larger distances, entanglement will be the larger, or the concurrence will be the greater. We did some results. We used some externally driven laser scheme like the Raman or the magnetic field gradient approach to excite our system from ground state to the excited state here. And again, I am not going to explain this mathematics here. We can determine the steady state concurrence by using this master equation. The left-hand side of this is going to be 0. We get this population of these dynamics. And similarly, for the 1 qubit system going to the 2 qubit system, if we do the similar things here, and we can find the concurrence from the master equation very simply here. And if we see that at larger distance, d is equal to 0 to 5 by 2 micrometer, we have that one larger results of the concurrence, steady state concurrence as well. Another good point was that one, we need the laser frequency, which is very, very small, 5.5 hertz. However, the scheme which we are using to excite this atom is also very satisfied that we can use the Rabi frequency of the 1 kilohertz. But we use 5.5 hertz, which is already met with the cold atom experiment results as well. However, I want to mention here that no one has predicted any experiment on that part on my model here, but I'm trying to collaborate with someone to have these experiments to get very good results here. And the last thing, due to the subradiant and subradiant interchange of subradiant and superradiant phenomena, we can see that we have obtained this phase gate. The basic purpose of this phase gate is to make a pi phase shift by blocking the excited state from decaying into non-decaying, due to which we have just the ground and symmetric state excitations or the decay rate, that one. With that, we are by using obviously the driving strength or these conditions which I have written here, not have a time to explain. We obtain this phase gate, which is not which does not have a good fidelity, but it's good with respect to that we have a distance in a micrometer. So these are the results for so far we have done with respect to this dark soliton qubits. No one other in the world is doing work on that system, and no one has performed experiment obviously on that one. But we are expecting that one day someone will do that experiment with the collaboration, which I am trying to do that one. So let me summarize my results. Okay, this is a very appealing candidate for the quantum memories and the quantum gates. And also I want to mention here that we did not see any dephasing effects here for this qubit yet, but I am trying nowadays to do that as well. And other many things I am trying to do that one. And I am expecting that we will in the future we will do some many good interesting resources whose importance is not yet glimpsed with respect to the quantum information theory. And we are expecting that this protocol will one day be seen as a crucial part of the quantum information protocols or the quantum information theory. Thank you very much.
Thank you, Mzama. Nice. Any questions? You have time for... Yes. Please go ahead.
So could I ask, I might have missed it, could I ask, how would you know that it is a superradiant state?
This is the fast decay of respect to that one. Gamma plus gamma. Spontaneous plus collective damping. That's right.
But how do you know that it is super radiant?
Because whenever you were in journal system, whenever you will find the life decay, or you will get the plotting of that one with respect to that time. For example, if I will show you here that one, that comes with the basically super radiant means to say the fast decay of the system of that with respect to that fast decay of that state. And here you will see that with respect to that state population, with respect to that time, if it is going to be faster than the other state, that means it has the faster decay than the other state, that one.
Mm-hmm.
So it comes with that one. So if you will see here, row AA is going to be the faster decay, row SS has a lesser decay than that one.
But typically, super radiance has a more specific meaning because it depends on the number of emitters.
Yeah. Yes. With respect to that one.
Oh, thank you.
Any other questions?
I have one question.
Yes, please.
Thank you for your talk. So you have considered 1D solitone and its shape is stable. So question is, do you have any plans to consider 2D solitones and see whether its shape is stable or not? 2D, two dimension.
Okay. When I was doing my PhD, one of my colleague has already done that one in the 2D.
So what was the output of that? Is it stable or unstable? Because in theory, 2D solitone is unstable.
Yeah, but they were predicting with respect to that vertices. They were using that in accordance to that one, and they obtained a very good result for that one as well.
Okay, so they are compensating this instability by using this vortices.
Vortices, yes.
Yeah, we need. I guess we can continue the discussion later. We need to move to the next speaker. Thank you, Mutawal, again. Yeah, there is plenty of time then in the offline to discuss.
Sure. Thank you.
So next speaker would be Dr. Moisiki. I don't see.
Yeah, he's there.
Is it here? Can you
Alexei.
Yes, I don't. It's just that is a black. Yes. Can you, Alexei? Can you share your slide? Can you hear me? Hello,
Alexei, you're muted.
Alexei.
Okay.
Yeah.
Good
Can you
afternoon.
hear me?
Can you share your slide?
Yes, please.
Yeah.
Yep. Still don't get it.
You're muted again. Alexei, can you hear us? Can you share your slide?
Good afternoon.
Good afternoon.
Yeah. Apparently, the technical problem appears just the moment I need to start to speak. Yet I can hear you, I can see you, and can I share my screen?
Yes, we see the screen. Yep.
Okay.
Yes, please.
Thank
go
you.
ahead. Quantum enhanced partial leak attack on a symmetric cipher. Please go ahead. Thanks.
Thank you. Good afternoon, ladies and gentlemen. My name is Alexei Moiseyevsky, and I want to present you a short speech about my recent research on quantum cryptanalysis and quantum enhanced attack on a symmetric SIS cipher. First of all, let's refresh what quantum cryptanalysis gives us. The most significant advantage can be taken for asymmetric cryptography because of exponential speedup of the Shor's algorithm. But even without taking into account noise limits of existing quantum computers, Shor's algorithm requires too many qubits, about several thousands, to attack RSA cipher, for example. On the other hand, For symmetric cryptography and hash functions, Grover's algorithm can provide quadratic speedup, but it is not such powerful as exponential, but it requires much fewer qubits because of shorter keys. For advanced encryption standard cipher, for example, it is about several hundreds of logical qubits, which potentially can be achieved in current decade. So Grover's attack is a little bit more realistic. Let's consider it. First of all, quantum Grover's algorithm is an algorithm for fast database search. It consists of two parts, the oracle function and amplitude amplifier. It provides O square root of n complexity if we can recognize solution in a polynomial time. N here stands for a number of elements in the database, for example, a full set of possible keys. At the first stage of the algorithm, the oracle have to flip face of the correct solution state component. On the figure, you can see the state omega, which is a component that corresponds to the correct solution, the state S, which is an equal superposition of all components, and the state S prime, that is a superposition of all components except the correct solution. Due to linear dependence, all these vectors lays in a single plane. The algorithm starts from S, and the oracle flips S to S with respect to S prime. That means it flips the face of correct component. Then amplitude amplifier appears and flips the resulting state with respect to S. And finally, we get to a step closer to the correct solution, omega. Note that amplifier has no information about S prime, so it can be the same quantum circuit regardless of the task. For a practical case, we want to perform an open text attack to the symmetrical cipher. We have an encryptor that takes an I flipped my slides. Yeah. Yeah, here it is. We need to stop here. Yeah. For practical case, we want to perform an open text attack. Here we have an encryptor that takes a plain text and a key as an input and gives us a ciphertext as an output. Then we solve an inverse problem. With Grover's algorithm around the encryptor, we want to get the keys from given ciphertext and plain text. Due to quadratic speedup of Grover's search, at presence of this attack, twice longer key is required to provide the same level of security. And here you can see a basic oracle for one-time paired cipher. We want to store plain text and ciphertext in the classical memory, then add plain text and ciphertext to the quantum key. It can be a superposition state with classically controlled Pauli X gates. If the key is correct, all qubits in the qubit register turn zeros, or after all qubit X gates, which are not shown here, to ones. Then we apply control Z gate to inverse the face of all ones component and apply all operations in the reverse order to restore initial key in the qubits. For practical oracle, we need to do all the same, but with a real encryption algorithm instead of simple XORs. For this purpose, we consider a simplified IAS algorithm. It is a toy model of widely used advanced encryption standard, but instead of 128 or 256 bits of key, it consists of 60-bit keys, 60-bit text, 2 rounds, and just like real IAS, of 4 prime elements, the encryption elements such as S-box, shift rows, mixed columns, and add key. To perform a quantum Grover attack on this cipher, we need to realize all these elements as quantum circuits to perform the encryption with a quantum state. And the first approach for this was made in 2018. And then at this paper, the S-box map was decomposed as an algebra map. Here we can see a quantum circuit that appears from the algebra behind S-box. It is a polynomial multiplier, which is a bit complex. And the worst thing about this quantum circuit is that at the end of this quantum circuit, we have A prime that is required quantum state, but also we have two sets of 4-qubit ancillas and the actually input A, and we have nothing to do with this input for all following quantum circuit. So the number of qubits required for this attack is get 4 qubits more after each S box. It is a really bad thing. We need to use fewer qubits. So the thing makes this quantum circuits actually impractical. Also, this is a possible quantum circuit for mixed columns without any ancillas, which is good, but also it is some set of CNOTs which can be simplified, actually. For example, we can try to rewrite the quantum circuit of 4 mixed columns map just from the explicit bit transformation. Here you can see it, and we can try to build the quantum circuit right from the rules at the left of the slide. Here it is. Here we can transform bits with a fewer number of CNOTs, but with respect to flipped order of the bits. And in 2021, the paper about basic quantum Grover attack for SIS was published. And here you can see improved S-box quantum circuit. It was improved with a tool named LighterR, and which is a tool to analyze inversible logic. And which is good about this quantum circuit that it doesn't use any ancillas and use just the same qubit set on the output, which is on the input. No ancillas, no extra qubits used. It is really good, and with this quantum circuit of S-box, we can try to build a full quantum circuit for SIS attack. Here is the quantum circuit for one route. Here we have a quantum register to store superposition state of the key and the plain text. We put plain text on the lower register, then apply first the 0 and the first key to the text with control nodes, then perform a coroutine named key extraction in the key register, followed by the transformations from the first round and the text. And at the end of this circuit, we have round 1 result in the text and the key number 2 and the key number 3. Oh. So I don't have a circuit with full attack, but with these circuits, one after another, we can perform 2 rounds, get encryption, then apply control Z gate to flip the correct key state component, do all the same in inverted order to get the one iteration of Grover's algorithm. We want to optimize the oracle. The known quantum circuit requires first 2 qubits from the attack, and it's quite a lot. We can't simulate 32 qubits on the GPU. It requires a bit more classical memory. So we want to analyze, can we reduce the required number of qubits, for example, with respect to a possible key leak. Here's a basic case of the usual attack. We have full key register, we have full text register, 32 qubits totally. And what if we have, for example, B1 key? You can see it is the top component of the key register. In the classical information, we have just 4 bits leaked of the key. It appears that if we invert the last CNOT in the key expansion coroutine, we can have the B2 and B3 round keys generated in the same set of qubits, but one after another in time. We have to use firstly B2 and then B3 to generate the result of the first round in text register. And then we need to store B0 in the key register, and in the same qubits we need to construct B2, B3, B4, and B5 in one register. We can do it for B2, B3, and B5. Here you can see the transformations required. But the problem is with B4. B4 has a coroutine X XORed with S box from X. And it appears that this transformation is not unitary. It is not reversible, so it can't be exactly represented as a quantum circuit. What can we do? We know what can we do. If the transformation is irreversible, we need to use ancilla qubits. But I don't have enough time to.
Yes, we have 4 minutes. 2 minutes. 3 minutes. 3 minutes. 3 minutes.
I need to. Yeah, we can overwrite the B4 problem with partial generation of the key parts B3 and B3 as boxed and B2, and we can construct scalable attack. For example, here is the main idea. We have text in the classical memory and key in quantum memory, and we want to work with the key nibbles one by one. For example, here we perform key expansion coroutine for the first nibble of the key, compared with the known ciphertext, and if the key is right, we write this to ancilla qubit. We have one in ancilla, and then we have data recovery, and we restore data, and once again do the expansion and 2 rounds for each of nibbles in the key register. Then finally we have all zeros in key register for the last nibble and 3 ancilla nibbles with ones if the key is right. So we have a longer quantum circuit, but we don't need text register anymore. So here's a quantum circuit for mixed columns required for that. So let's skip it. And I thought I have 15 minutes for my speech, and it seems like I don't have enough time to explain this table, but the key idea is that we perform full encryption procedure with all nibbles one by one in the same qubits. It allows us to use just 23 qubits instead of 32 in general case of attack, even if there is no key leak. 18, 17, 15, or 11 qubits for attack with partial key leak. And the most important conclusion is that this is enough. This is small enough to use GPU accelerated simulation, which, for example, NVIDIA Tesla A100 with 40 gigabytes of video memory can simulate 29 qubits. It is enough. And this algorithm is scalable. We can try to perform this for the same logic for full IES, and this is a place for further research. Thank you for attention. Yes.
Thank you so much, Alex.
Mm-hmm.
So yes, please. There was already one question.
Alex, you have assumed in the simulation that the gates are all fault, error, not error prone. So what in real quantum computers there are lots of errors in the gates.
Of course.
And how would that affect your recovery?
Of course, our algorithm is too long. The depth of the quantum circuit is too long to be performed on the real quantum computer. But with this algorithm, for example, we can consider the case when the 3 quarters of the key was leaked, and then we need only 11 qubits to perform this attack. And for example, with 400 qubits on the last IBM quantum computer, we can perform quantum correction and quantum error correction and error mitigation. So I think this algorithm can be performed on the in experiment in 5 years, maybe in 5 years. Of course, we need a better physical qubits, we need a logical qubits for that, but we can reduce required number of qubits in some cases, in case of partial key leak with this algorithm. Also, we can use GPU accelerated simulation to discover the ways to perform error mitigation exactly for this algorithm, for example.
Okay. Thank you.
Thank you. Any other questions? If not, we can thank all the speakers of this session again, and we'll resume again tomorrow. Thanks, everyone.
Thank you.
Thank you.
Cheers.
Thanks.